Surprise! So this will be one of your unforgettable maths journey. And in this video, we are going to discuss about taking cosine of a matrix. And the intended audience for this video is those of you who are completely surprised by we can even take cosine of a matrix, right? Doesn't like to take a cosine the input should be an angle, because we have always defined cosine as the ratio of base over hypotenuse, right? The cos theta is base over hypotenuse, right? So how come we take cosine of a matrix? So if this puzzles you, so you are at the right place, because we are going to discuss how to do that in this video. So now notice that we can also define cosine from the Taylor series as well. So we know that like cos theta, the Taylor series for this is theta minus, sorry, not theta, sorry, 1 minus theta square by 2 factorial plus theta to the power 4 by 4 factorial minus theta to the power 6 by 6 factorial and so on, right? Basically this sum from k equals to 0 to infinity of minus 1 to the power k by k factor, sorry, minus 1 to the power k by 2k factorial theta to the power 2k. Yes. Okay, now if we like suppose that the definition of cos theta is this Taylor series, now we are able to generalize theta even to the matrices. Even if theta is a matrix, with this definition we will be able to compute the value. Okay, so if you're wondering how, okay, so if I just substitute theta as 733 minus 1 over here, 733 minus 1, this will just be k from sum from k equals to 0 to infinity minus 1 to the power k by 2k factorial. This will just be our 733 minus 1 to the power 2k, right? And we can definitely find any power of matrices, right? Because like let's say if you want to find the second power of matrices, that just means multiplying matrix twice, right? And if you want to find the nth power, we can multiply it n times, right? N times. And we definitely know how to multiply two matrices, right? So this can definitely be done. Even though this might be tedious, this can definitely be done. So if you just compute the second power divided by 2 factorial with the minus sign plus fourth power divided by 4 factorial with plus sign minus. So if you just compute this long sort of computation, we will definitely get the answer. So this does show that this can be done. But the only problem is, how will you even find the 100th power of matrix? Is that doable in a single day? Yes, that's actually doable within 10 or 15 minutes. We don't even need a single day. Like there are some ideas which help us do that. Okay, so from here, now we just have a problem with how to find any power of this matrix, right? Let's say nth power of this matrix. If we solve this problem, then we will be able to evaluate this series, right? And we will be able to find the value of the cosine with matrix as its input. So I guess this is clear till now. Now let's see how do we find the nth power of a matrix. Now this idea is related with the fact that like for almost every matrix, not every, for almost every matrix, there are some vectors a1, b1, such that if you multiply this matrix with the vector, the only thing that happens is this vector will get like scaled. This vector will just get scaled. That means multiplied by a scalar, right? Now let me just show you like one example for this one. So for this one, 733 minus 1. If you multiply this by 3 1, your answer would be 7 times 321 plus 324, and then 9 minus 1, 8. So you see that if you just take the 8 common, this is just a scaled version of this vector, right? You see that this when this matrix was multiplied by this vector, this just scaled by 8. So this is not a magic. If you know about matrix as a transformation, right, then this might seem kind of obvious. But for now, you got the idea, right? You got the idea, right, that for every matrix there are some vectors Like basically for n dimensional matrix, like normally there are n such vectors. And for this is two-dimensional matrix, so there will be two such vectors. One of them is this one, the other we'll find out later in the process. Okay, so yeah, you got the idea that like for every matrix, and this idea will be helpful because the multiplication of this matrix is captured by the single value lambda. This is the special value. You guys know that this is a special vector. These are special vectors because the reason is the multiplication by this matrix is captured by this single value lambda, right? And there are some connections about this value and the matrix which will later which we will later explore, right, in the further like courses as well. But for now, you should know that like if we are able to identify this special vector, then we will be able to capture this matrix using this value. Now again, the benefit of like knowing that this sort of thing happens is, now let's say if I want to multiply by this matrix twice with this vector, now see the magic. Now if I want to do this, okay, now first of all, if I multiply these two, if I multiply those two, I know that I will just get, let's say this is lambda 1 times a1 b1, right? Now again, I get this is lambda 1, I can take that ahead. So now again, I have the same multiplication, 733 minus 1 times a1 b1. Again, I know that that's just going to be lambda 1, right? So this is just lambda 1 times a1 b1. So that's just lambda 1 square times a1 b1, right? So we saw that if we have like two such matrices being multiplied, if we have this square, this will just be same as lambda 1 square times a1 b1. You saw that? That's pretty beautiful. Again, if you introduce another like such matrix such matrix as being multiplied, this will just be lambda 1 cube. So yeah, if you just go on increasing like this matrix, if you just go on like n matrix multiplied by n matrices in front of this one, right? This will just be equals to lambda 1 to the power n a1 b1. And this is a really powerful result. I can also write this as lambda 1 to the power n a1, right, if you want it to be. And this is a really powerful result because this nth like power of this matrix is captured by this single value, and this is really easy to calculate, right? Even though this might be hard, this is easy to calculate. Now how do we extract that, like how do we extract the nth power of matrix from the single value? That's the question. Now like we will go on that. Now like earlier I told that for two dimension there will be two such special vectors, like this a1 b1, this is special vector. So let's say the other vector is 733 minus 1 to the power n times a2 b2, right? And this also has the same property that this will just be scaled when multiplied by that matrix, right? So this will just be lambda 2 to the power n a2, lambda 2 to the power n b2. Okay, now we know that, now we know this, right? Now I can also write this in a different manner. Like I'll just show you. Like if I want to write both of this information in a single equation, I can write this as 733 minus 1 to the power n, and then a1 b1 a2 b2. Then I guess you guys know that if I do this multiplication over here in the like first column, the result will basically be this matrix when it's multiplied with the first column over here, first column vector over here. The result will be the first column vector over here. And we know that when this matrix multiplies a1 b1, the result is lambda 1 to the power 1 a1, lambda 1 to the power n b1, right? Now when this matrix, again this matrix multiplies with the second column vector, this will basically give us the second column vector over here. And we know that when this matrix multiplies with a2 b2, the result is lambda 2 to the power n a2, lambda 2 to the power n b2, right? Okay guys, now I will just try to write this answer in a slightly different way. How I will write it is, now I will write this as a1 b1 a2 b2. Now lambda 1 to the power n 0 0, lambda 2 to the power n. Now notice that this is valid because So first of all, when this multiplies with like this row multiplies with this column, only a1 will be multiplied by lambda 1 to the power n, and other will be 0, right? So our first element will just be a1 lambda 1 to the power n, right? Now after that, when this first row, okay, let me just erase this. Okay, now after that, when this first row now multiplies with this, the second column, this will just be a2 lambda to the power n, which is exactly what it's here, right? And now again, if this multiply this first row, second row multiplies with first column, this will be b1 lambda to the power 1, which is over here, right? And again, if you try to multiply this second row with second column, this will be b2 lambda to the power n, which is over here, right? So yeah, that's valid. That's valid. Okay, now I guess you should be able to do this on your own as well, right? If you this will if you just multiply like by this diagonal matrix, so basically this number in the first column will like basically just I mean number in the first row will just, I guess you got the idea. There's a generalization as well, but let me not go into that. I guess you got the idea that this works, right? Okay. So now what we have is 733 minus 1 to the power n times a1 b1 a2 b2. So for a1 b1 and a2 b2 being those special vectors, this will be equal to a1 b1 a2 b2 times lambda 1 to the power n 0 0. Now the reason I did this is I wanted to make these two matrices same, so that's why I broke this matrix as a product of these two matrices. And like the breaking a matrix as a product, this is actually a very like common ideas, and yeah, you will be familiar as we go learning the mathematics. Now notice that if I take this to the other side over here, this will turn into inverse, right? Yeah, I can basically, we know that if let's say m a is equals to b, if I take a to other side, this will be m is equals to b times a inverse, right? And also note that I cannot take a over here in front. Also note that because like in matrix, because in matrix the order of multiplication matters, right? And more formally, this can actually be done as, let's say, m a getting a inverse in the both like left sides, and this will just be I, and this will be a inverse, m is equals to b a inverse. And since order matters, you cannot just say that this will be equals to a inverse b. Like it's not like numbers, so you need to be careful about where the location as well, right? So that's an important thing. So yeah, definitely you cannot just take it over here, you cannot just take it over, let's say, here, and then multiply these two, get I, and then say that these two are equal. That's not valid, guys. So I just wanted to remind you about that, since it's a matrix. Now I'll just take it to the other side. Then what we get is, then we get 733 minus 1 to the power n will be equals to a1 b1 a2 b2 lambda 1 to the power n 0 0 lambda 2 to the power n, and then a1 b1 a2 b2 inverse. Now guys, see, look at the result that we have got. Now these three are just three different matrices, right? And we can definitely multiply them. There's no problem in just, this is just like around 5 minutes work. First multiply these two matrices and multiply these two matrices, right? And the result is the nth power of this matrix. You see that? That's really powerful, right? Now we can just find nth power of any such matrix by just multiplying these three matrices. And that's a really powerful result. You see that? So yeah, that's a really powerful result. And now after we have got this result, now the only problem is how to find those special vectors a1 b1 a2 b2, right? And how to get those special numbers lambda 1 lambda 2, because only then we can use this result that we have got to find the nth power, right? Okay, so now let's get let's get to that. Now how we can find that. Yeah. Okay, so now if you want to get to that, okay, so now let's get back to how we define these vectors and numbers. Now, So initially we defined these vectors as like these vectors a1 b1 and a2 b2. We defined these vectors and these numbers as in this way, right? Like first of all, like for a matrix there will be a such vector such that when we multiply it, this will just get scaled by a number, right? We did that to get to these matrices, right? So from this definition we'll try to find that. Now there's a matrix. We just know a matrix that's defined. Rest of them are unknown to us, right? Now first of all, I will just take both of them to this side, right? Now guys, now like I wanna take b vector common, right? But guys, like if I write it like this will be completely wrong, guys, because this b vector is at the back side, at the right side. So if I just write it like this is b vector times m, and we know that like a matrix multiplication like is on like commutative, so this is not true. So guys, I want to aware about that because many people make that mistake. So I have to take b vector common, and this will be m minus lambda, right? And again, you might have a confusion. This is a matrix. This is a number. So how do we even subtract to matrix? Let's say 1, 2, 3, 4 with the number 5. How do we do that? Okay, for that we again have a solution. The solution is okay. Now in our case, this b vector is like two-dimensional vector, right? Now this b vector it's same as, even if I multiply this by 1 0 0 1, this 2 by 2 matrix, this will still be 1 0 times 1 2, which is 1, 0 1 times 1 2, which is 2. This will be same, right? So what I can instead do is, first of all, I can write this as, this v vector can be written as I matrix times v vector, right? Now only if I take v vector common, this will be m minus lambda I. And now this is also a matrix minus matrix, so that's valid. And this is the vector, and we can definitely do a 2 by 2 matrix times a vector, right? So yeah, this is how we can make sense, right? Okay. Now after this, okay, now how do I use this equation to solve for like b and lambda? That can be the question in your mind, guys, right? Now I can notice something over here. So let's say like normally, let's say if I have 2x is equals to 0, what I would do is I would just take this 2 to other side and half times 0. So x will be 0, right? So we do such things in normal algebra, right? Now if I try to do that over here, now this, if I take b to other side, this will be 1 by m minus lambda I. Since and I can do this because we know that both of them are positive, right? So both of them are like positive matrices, like I mean, yeah, no, non-zero matrices, not positive, non-zero matrices. So definitely they're definitely like none of them is 0, right? Since both of them are like non-zero matrices, none of them is 0. So I can definitely take this down. And like guys, like this might seem non-intuitive at first. Like how can just two non-zero matrices like multiply and give 0? Like is that even possible? Yes, guys, that's actually possible, and I can actually show you that, I guess. I'm not sure if I will be able to get an example, but I think I can show you that. Mm, hmm So let's say if I have 1 1 1 1, right? Then I have, I don't know, 1 minus 1 minus 1 1. Will this work? So this will be 1 minus 1 minus 1 plus 1, 1 minus 1 minus 1 plus 1. So see guys, so even though both of them were non-zero, this is 0 0 0 0 matrix, right? So yeah, it's completely possible that even by multiplying non-zero matrices we can get 0. So you need to satisfy some certain properties which we will discuss over here, but yeah, don't get surprised with this result. Okay, now since we know that these two are non-zero matrices, and yeah, it's possible that the result is like a 0 matrix, right? So this will be this. So this is also, see this as a 0 matrix, like matrix, guys, like not as a constant 0, because the matrices, I mean, as a zero vector, because that will be our result, right? See it as zero vector because that's the going to be the result. There's not going to be a scalar result. Okay. Yeah. Okay. Now we can do this in algebra, right? If I try to do similar thing over here, since we know that they are non-zero, if I just try to take it to other side, so what will happen is this will just be m minus lambda I inverse times 0, right? Now suppose its inverse exists. If its inverse exists, right, if that exists, then its inverse matrix times 0 matrix, like anything multiplied by 0 matrix is just 0, right? So if we suppose that its inverse exists, our b vector is just 0. Like we get that result, but clearly b vector like would not be a 0, right? I mean, if b vector is a 0, again there would be a problem. Like I mean, if that's the 0, so 0 0 0 0 again. Like I mean, this whole results is assuming that a1 b1 are some numbers. So that will definitely be I mean, this whole thing is assuming that a1 b1 are some non-zero numbers, so that will be a problem. So that means that if we don't want our p vector to be just 0, we need to assume that this m minus lambda I does not have an inverse, right? I mean, yeah, does not have an inverse, right? And for a matrix to not have inverse, to not have inverse, to not have sorry to to not have inverse, to not have inverse, their determinant should be 0, right? I guess you guys know that, because the inverse of matrix is just defined as like just determinant of the matrix times adjoint of this matrix, right? So yeah, if this is 0, then the result is just undefined, so we cannot find inverse. I guess you guys know that, right? So yeah, if we do not want our b vector to be 0, yes, which we exactly don't want, because this b vector should be numbers for this all whole thing to work, right? Over here, the a and b should be some numbers, not just 0, right? I mean some positive numbers. So yeah, if we want that, this matrix should not have any inverse, right? And for it to not have inverse, its determinant needs to be 0, right? Now yeah, so from this equation now we'll be able to solve for lambda, and then we'll be able to solve for b as well. Okay, now this is basically a condition to find lambda. And now let me reveal what this lambda and these vectors like name is. This is called eigenvector. Eigen basically means itself, because these vectors basically give themselves after multiplication, right? Just a square multiple of themselves. So yeah, this is called eigenvector and eigen. Sorry, this is called eigenvalue, not eigenvector. Eigenvalue and eigenvector. Yeah. So this is kind of name reveal or face reveal like that we do in the gaming section. So yeah, let me do this, because yeah, I think I need to spell their names now. Okay, now we need to find this lambda, which is our eigenvalue, right? Now, like for this, now in our scenario, and this symbol is basically saying that to take the determinant. Now, in our scenario, like if you want to find lambda, we need to definitely substitute the m over here, right? Okay, our m is 7331. 733 minus 1. In our case, our m is 733 minus 1. Alright? Okay. So, like if we try to evaluate this determinant of, to find the lambda, 733 minus 1 minus lambda times 1001, right? And yeah, determinant is equals to 0, so this will just be 733 minus 1 minus, this will just be lambda times 0 is just 0, lambda times 0 is just 0, lambda times 1 is just lambda. You need to multiply by that scalar to every element. So now this will be matrix of 7 minus lambda, just 3 minus 1 minus lambda, right? Determinant is equals to 0. Now this will be 7 minus lambda minus 1 minus 1 minus lambda minus 9 is equals to 0. So this is just minus 7 lambda plus lambda square minus 9 is equals to 0. This is lambda square minus 6 lambda minus 16 is equals to 0. So this is, you know how to factorize that, right? So this is lambda square minus 8 lambda plus, guys, this is easy stuff, so I'm just doing it quickly, right? Okay. And so the factor like this, lambda times lambda minus 8 plus 2 times lambda minus 8 is equals to 0. If you take lambda minus 8 common, this will be lambda plus 2 is equals to 0. Now either lambda is equals to 8 or lambda is equals to minus 2. Basically one of the possible answer, lambda 1 is 8, or the possible answer lambda 2 is negative 2. Okay, we got this right. Okay, now corresponding to this eigenvalues, we also know that, like for this eigenvector a1 b1 we have eigenvalue lambda 1. For this eigenvector a2 b2 we have eigenvalue lambda 2, right? So we need to find the eigenvector like a1 b1 for lambda 1, right? Now again we will just again get back to the definition to find these things. Now again our definition was like previously, m times b vector should be, like, let's say a b1 vector should be lambda 1 times b1 vector, right? Our m is just 7 3 3 minus 1, 7 3 3 minus 1. Our b1, let it be a1 b1, should be equals to 8 times a1 b1, right? Now if you just multiply and like equate the both sides, this is just gonna be 7a1 plus 3b1. This is 3a1 minus b1 should be equal to 8a1 plus 8b1, right? And so this will just be 7a1 plus 3b1 is equals to 8a1, which is just same as negative a1 plus 3b1 is equals to 0. Now over here this will just be 3a1 minus b1 is equals to 8b1, which I can write as 3a1 minus 9b1 is equals to 0. Now guys, if you analyze this solution, you will basically get infinite solutions for these two equations, and that will always be the case in finding the eigenvectors, right? And you don't even need both the vectors like to find solution, like even one is enough. So yeah, so you can just analyze the solution actually. So for this to be 0, this just needs to be like 3 comma 1, right? If a1 is 3, this is 1, this is minus 3 plus 3, which is 0. Over here also this is 9 minus 9, which is 0, right? Okay, so and 3 comma 1 is one of the solutions, but also notice that even if I multiply this by any number t, this will just be again minus 3t plus 3t, which is also 0, right? So yeah, there will be infinite solutions which will just be a multiple of 3 comma 1, right? And obviously 0 comma 0 is a solution which is just trivial solution, but over here we had assumed that our b vector is not 0 vector, so we can definitely not take this solution, right? Because we had earlier assumed over here to get this determinant 0 that b vector is not 0 vector, right? So yeah, we cannot do that. So yeah, I mean even if you do that, there will be no, I mean this whole thing would not be possible, right? So yeah, there's no point taking taking this trivial solution of 0 0. Okay, so yeah, there are infinite solutions, but like one of them would be enough for us. Like we don't need this t, just the simple 3 1 will be enough for us. Okay, so yeah, so now we got the solution for a1 b1 in this. Okay, wait. Okay, we got the solution. Where is my pencil? We got the solution for a1 b1 in this case to be 3 1, right? And this is the simplest solution which we are taking. Oh, this will also work, but we just need the simplest one. So yeah, so we got that for lambda 1 is equals to 8. Our required eigenvector a1 b1 is just 3 1. Now let's go with another case. mb1 is equals to mb2 is equals to lambda 2 times b2 vector. Our am is just 7 3 3 minus 1 times a2 b2 will be equals to our lambda in this case. And guys, this 3 1 vector is exactly the same that I had predicted earlier. Over here, did you notice that like I had multiplied this 7 3 3 1 minus 1 with 3 1 to get this 8 times 3 1, right? And exactly this is our eigenvalue, this is the eigenvector. See, so actually like maths can help us make predictions, right? This might have seemed like unobvious at first, this might have seemed like magic, but now it's just math that's giving us these results, right? We got it through entire calculations. Okay, now this is, we know that lambda 2 is negative 2, a2 b2, right? And this is now 7a2 plus 3b2. 3a2 minus b2 is equals to negative 2a2 negative 2b2, right? So yeah, now if you just try to equate the corresponding components, this is 7a2 plus 3b2 is equals to negative 2a2, which will just become 9a2 plus 3b2 is equals to 0, and this will be 3a2 minus b2 will be equals to negative 2b2, which will just be 3a2 plus b2 is equals to 0, right? Again, just like earlier, like it's enough to solve one of the equations, right? Because basically they are just infinite solution, they are kind of coinciding lines, right? Okay, now notice that the solution will just be a2 should be equals to 1 and next should equals to negative 3, right? So 9 minus 9 is 0, 3 minus 3 is 0, yeah. And also like all these like multiples of t of this vector of this like 1 minus 3 are solutions, but we just need a simpler solution. Any of them would basically work, but we don't need them. Okay, so yeah, so we got that this vector a2 b2 is just 1 minus 3, right? And this is for the case, where lambda 2 is negative 2, right? Okay guys, now we have all these values, and let's get back to our original this formula over here. Now let's substitute them. Whew. Okay, now over here, now I can say that this 7 3 3 minus 1 to the power n, this is just, so our a1 b1 is, what was that? A1 b1 vector as 3 1 1 minus 3. And guys, also you can take this as a1 and this as a2 b2, doesn't matter the order. 3 1 1 minus 3. This is just 3 1 1 minus 3. And now lambda 1. Okay, now since this is a1 b1, corresponding to this a1 b1 we have lambda 1 as 8, and corresponding to this a2 b2 we have lambda 2 as negative 2, right? And both are raised to power of n. And yeah, over here we have again this a1 b1 a2 b2 to the power inverse, right? Okay guys, now we saw that how we can find nth power of matrix, and we will not multiply it right now, we'll do it later on. Right now let us leave it as it is. Now our problem was to find the cosine of this matrix, right? Of this matrix 7 3 3 minus 1, right? And I already told you that this should just be equals to sum from, oh wow, low battery. Let me just charge it, guys. Wait. Let me just charge it. I guess you guys are enjoying it, right? Okay. So this will just be sum from k. Isn't it charged? Okay. Sum from k equals to 1. Sorry, from 0 to infinity of negative 1 to the power k by 2k factorial, and then this will just be x to the power 2k. So in this case our x is this matrix 7 3 3 minus 1 to the power 2k, right? Okay, now again this will just be sum from k equals to 0 to infinity negative 1 to the power k 2k factorial, right? And we know that this would just be 3 1 1 minus 3 times, so 8 to the power 2k 0 0 negative 2 to the power 2k, right? And then 3 1 1 minus 3 inverse, right? Okay guys, now this is just a constant in product, so I can definitely take this out of the sum, right? So this will just be 3 1 1 minus, this will go out of the sum because this is a constant it's in product, right? I guess you guys know, like let's say if I want to sum this per I, and if I have a times I can take a out, right? And I could just sum the i's, right? So I'm doing the same thing over here as well. I'm doing the same thing. Okay, over here now this will be sum from k equals to 0 to infinity my negative 1 to the power k by 2k factorial, right? and this is just 3 1 1 minus 3, right? And then 8 to the power 2k, 0 0, negative 2 to the power 2k, right? And then, oh wait, I'm sorry, I have already taken this out. Sometimes like the lagging occurs. So 8 to the power 2k, 0 0, negative 2 to the power 2k, and this is just 3 1 1 minus 3 inverse. Now guys, notice that this is also constant in product, right? But I cannot take this out over here because just like I said earlier, the order matters in matrix multiplication. So how will I take this out of the sum is, I will basically take that like in the back direction over here. Take that common, but in the like right, in the like rightmost portion, no, not ahead. That's because it's matrix, and matrix multiplication is not commutative. So by 2k factorial, now this is 8 to the power 2k, 0 0, minus 2 to the power 2k, right? Okay, now since this is just a constant for the matrix, right? No, not for the sum, for the matrix. This is just a constant, right? And this can definitely go inside the matrix, right? So yeah, that's just a scalar, and I will take that, I will multiply by that scalar to every term of the matrix. So if I do that, this will be 3 1 1 minus 3, and this will be sum from k equals to 0 to infinity. Now it will be minus 1 to the power k by 2k factorial times 8 to the power 2k. Now this will be like 0 times this number will just be 0, right? Even though 0 is multiplied anything, it doesn't matter, it's also be 0, right? And over here this will be negative 1 to the power k by 2k factorial, negative 2 to the power 2k, right? Okay, and this times we will have this 3 1 1 minus 3. Oh, also there should be inverse, I'm sorry. Okay guys, now notice that I'm summing the matrices, right, for different values of k. And I guess you guys know that, let's say if I'm summing a1, let's say a1, b1 c1 d1, plus let's say a2 b2 c2 d2, plus let's say a3 b3 c3 d3. We know how this going to work, right? Just the first components will be added, right? The second components will be added, right? The third components will be added, right? The fourth components will be added, right? So yeah, over here also, while solving this matrix, the same thing is going to happen. The same thing is going to happen. All the first terms will be added, all the second terms will be added, all the third terms will be added, all the fourth terms will be added. And if we do that, now what we are going to get is, if we do that, this will be 3 1 1 minus 3, and this will just be sum from k equals to 0 to infinity of negative 1 to the power k by 2k factorial 8 to the power 2k. Now again, sum of 0 is just 0, sum of 0 is just 0 over here. Sum from k equals to 0 to infinity of negative 1 to the power k by 2k factorial. This is negative 2 to the power 2k, right? And this is just 3 1 1 minus 3 inverse. Okay guys, now notice that this is just cos 8, right? Basically cos of 8 will just be sum from k equals to 0 to infinity of negative 1 to the power k by 2k factorial, and then 8 to the power 2k, right? And that's exactly the case over here. So yeah, so this has simplified now. So this has simplified to 3 1 1 minus 3, right? And then over here this will just be cosine of, why is it becoming 2? Okay, wait, I had used the wrong pen. Okay, now this will just become 3 1 1 minus 3. Now this will be cosine of 8 0 0, cosine of negative 2, right? That is obvious from here as well, because it was even power, the negative 2 would have eventually gone. Also because cos even function, that would eventually go, right? So yeah, Now we need to multiply these three, which is not a difficult task at all. So first of all, let's find the inverse. So 3 1 1 minus 3, cosine of 8 0 0. This will just be cosine of 2. And now determinant will be, I guess you guys know how to find inverse of 2 by 2 matrix, right? So inverse of A B C D will be 1 by determinant will be AD minus BC, right? Determinant will be AD minus BC, and then we need to have adjoint, which will just be, okay guys, now what? Okay, it will be DA minus B minus C. This will be an adjoint, so this will be an inverse of the matrix. This will just be 1 by minus 9 minus 1, and minus 3 3 minus 1 minus 1, right? These two interchange and these two are negative. Okay, so now we need to I can take the constant in front, so minus 1 by 10. And now guys, and I cannot just swap the matrix order, right? Because this is not commutative, always remember that. So cos 2, now this is negative 3 negative 1 negative 1 3, right? Now we can just multiply one by one. We can just go on multiplying. First of all, let's multiply the last two matrices. So that will just be negative 3 cos 8 plus 0, and this will also be negative cos 8 plus 0. So this will just be negative cos 2. And I guess you guys know how to multiply, right? Like I can assume that definitely, right? Let's say this is a1 b1 c1 d1 times a2 b2 c2 d2. The multiplication will just be a1 a2 plus b1 c2, a1 b2 plus b1 d2, c1 a2 plus d1 c2, c1 b2 plus d1 d2. So this is how the matrix multiplication for 2 by 2 matrix is defined. The negative cos 2, and this is 3 cos 2, right? Okay, now for this one, this is negative 1 by 10. So now this will just be negative 9 cos 8 negative cos 2, right? And negative 3 cos 8 plus 3 cos 2. You can see that, right? First of all, I just multiplied this with this, and then this one with this one. Yeah, now I will first multiply this second row with first column, and then second row with second column. That's how it works. So now this will be negative 3 cos 8 plus 3 cos 2, right? And then negative cos 8 minus 9 cos 2. Okay, so now again, if I like multiply that by like negative 1 by 10, so that will just be 9 cos 8 plus cos 2 by 10, and then 3 cos 8 minus 3 cos 2 by 10, 3 cos 8 minus 3 cos 2 by 10, and this is cos 8 plus 9 cos 2 by 10. Now let me compare this with the answer given by the Wolfram Alpha calculator. I will upload the link of the like answer by Wolfram Alpha in the comment section, but for now I will just access it. Okay, so the answer was 9 cos 8 plus cos 2 by 10, 3 cos 8 minus 3 cos 2 by 10, 3 cos 8 minus 3 cos 2 by 10, cos 8 plus 9 cos 2 by 10, right? And in the decimal form, that will just be negative 0.172, 0.0811, 0.08, negative 0.389. Okay, that will be the answer. Now guys, just like I told in the beginning, if you had just like taken some days or months to do it rigorously by just finding the powers like on your own and just go on adding and adding and adding these things, you would have definitely arrived at this answer. And see like how maths reduced the works of a lot of days into a like single 30 minutes video, right? So that's why maths is powerful. Maths can reduce a lot of works. Maths can like make general formulas. I mean, like math can generalize things and do magics. So yeah, now we finally got our answer. So this is it. This is the cosine of this matrix, and notice that the answer is also a matrix, and that's how it works. Okay, so we have done this, and before I end this video, let me go with some like mathematical like details or like formalizations of this concept, right? Now, just as I told, first of all, I have already introduced that this is called eigenvector and this is called eigenvalue. And also something more that you need to know about the terminology over here is, so yeah, in this format, basically this matrix 8 0 0 minus 2, where this is basically lambda 1, this is called basically lambda 2. We call this a D, which stands for like diagonal matrix, okay, because like only diagonal elements are there, rest are zeros. So if the all the elements except the rest are zero, we call the diagonal matrix. And this element, which is just the collection of two eigenvectors, right, a1 a2 and b1 b2, this is usually denoted by p, so this will become p inverse, right? And yeah, like why now, like generally while solving a problem, the only focus is to find the eigenvectors and the eigenvalues, right? Because once you find them, you can find the p and d, because p is made of a1 a2 and d is made of b1 b2, right? And also yeah, d is just the vector of the eigenvalues, right? Eigenvalues in diagonals and rest are zeros. And the last one is p inverse. We saw in this video that like m to the power n is just like a d to the power n. So basically if you raise a diagonal matrix to the power of n, just the diagonal elements will be like raised to nth power. So I can also I can write this as I can write d, I mean I can write this as also as 800 negative 2 to the power n, because if you just try to compute like n for n is equals to 1 or 2, you will see why just the diagonal elements will be raised to nth power. So in this video we saw that this holds true, right? And not just these, not just this, because if you substitute n as 1, this m is equals to p d p inverse also holds true. Yes, you can see that if you substitute n as 1, this also holds true, right? And normally, like while doing this sort of raising matrix to power n, first of all, people express m as pdp inverse, and then like people now to get to this result, what people argue is m square will just be pdp inverse multiplied twice, right? And then over here, this since it's associative, I can write this as PD P inverse PD times P inverse. So this is just PD ID P inverse, and I just identity matrix, which is just of matrix times inverse is this identity matrix, right? You know that. So this is just again P or D square P inverse. So we saw that our m square is just P D square P inverse. Similar by induction, we can argue that m to the power n is just P D to the power n P inverse. So yeah, you can also go it from this thing that matrix can be written as the product of P and the D, right, in the form of PDP inverse, and from there also you can go with this formula. But yeah, either way is actually same, and I just wanted to give you this like formal arguments, formal like definitions, like the what they are called. And yeah, so yeah, definitely like that might be important if you are dealing with textbook. But yeah, but knowing the concept is actually more important, and that's what we did in this video. So yeah, this was the mathematical journey I promised you at the beginning, right? And just like this child, get curious, keep learning, and yeah, that it is. So hope you enjoyed the video. Thanks for watching. And if you love such maths content, I look forward to seeing you in my upcoming videos too. Okay, so if you want to take a screenshot, you can take a screenshot now. Okay, wait, if you can take a screenshot now, you can again take a screenshot, and you can again take another screenshot, I guess. Yeah, I think that this should work. Yeah, that's it guys. Goodbye.